So now we're in section 4.3, logarithmic functions. Okay, so far we've been talking about the exponential function. F of x equals a to the x. A is greater than 0. So it's a positive number, positive real number. But it's not equal to 1, just because that's not a very exciting function. We've already talked about that it is 1-to-1, and therefore it has an inverse. So a logarithmic function is the inverse of the exponential function. So if you have f of x equaling a to the x, its inverse is log base a to the x. Okay, we're going to be talking about this for sure. So just a thought, just a reminder, because a function and its inverse have, these special connections, we want to be reminded that for this function and its inverse, they're going to be symmetrical over the line y equals x. So we're just remembering our properties of inverses that we talked about a while ago. So if we think about y equals x, I'll just go ahead and put that here. Dun, 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 dun. Okay. More or less function y equals x. Then let's remind ourselves from the first section here, we have the values for 2 to the x. We already did these. I'm not taking them out of thin air. You should have these in section 4.1. And then we remember that because of the reflection over the line y equals x, that a function and its inverse have their x's and their y's switched. So I don't actually need to do any work here. I'm not asking you to do anything, but just remember that fact so that we can find the values for our logarithmic function. Okay, which again, I'm going to talk about in just a minute. Okay, so I can put on my 2 to the x there. I know what that is already because we've done that. So go ahead and put on your 2 to the x, and then if you want, go ahead and put on your values for this log function that we're going to be talking about, and then we can connect the values together. Okay, so I'm just taking myself back, 2 to the x. I already know what it looks like. We've done it before. Okay, so whatever you do, it should be symmetrical over the line y equals x. So when I put my other values on, I see that I have 1/4 negative 2, so I'm down here. Then I have 1/2 negative 1 right here. I have 1, 0, 2, 1, and 4, 2. So our logarithmic function is going to have this shape, and then it's going to head down like this towards the y-axis there. So do notice the symmetry that's occurring because they are inverses. So that's the focus for the moment. Okay. You can kind of already see what the properties are going to be, maybe, of the logarithmic function, just because you can see from our picture here what the domain is going to be, what the range is going to be. We also remember that the domain and range are switched for a function and its inverse. So that's helpful because of what we know about our exponential function. Just a reminder. So taking a look at what we have here, what does it mean? We're remembering that we have our basic exponential function here, y equals a to the x. So if we take x and we put it as our exponent with base a, then we take the log of that thing, the log base a of that thing, that's how it's read, log base a of a to the x. We're going to come out with x. We're going to talk about why this is. A logarithm is an exponent. A logarithm is an exponent. That is something to absolutely remember. A logarithm is an exponent. It is the exponent of base a that produces whatever is inside the logarithm. Okay. So we'll take a look at some examples here to get comfortable with it. We have log base 2 of 8. The question that is being asked here is, what is the exponent that you would put on 2 to get 8? And one of the ways to solve logarithms is to rewrite, if you can, which is not always the case, but if you can, rewrite the inside as your base to a certain power. So if I have base 2 of 8, if I can rewrite 8 as 2 to a power, which I can, because 8 is 2 cubed, then I have my answer. So 3 is the exponent of a of 2 that gives me 8. And that's how we read that. Very similarly, I'm going to come down here and do the log base 10 here. So we can rewrite 10, we can rewrite 100 with a base of 10. So we rewrite the inside as 10, and then we think 10 to what power gives me 100? Well, that is 10 squared, so our answer is 2. So 2 is the exponent to which we raise 10 to get 100. Logarithms are exponents. Now, sometimes they get a little thought-provoking, I'll say. Here we have 7, the square root of 7. All you have to remember is how else you can write the square root. So you want to remember that the square root can be written as a rational exponent, raising a power to the 1/2. So when I see the square root of 7, that's the same as 7 to the 1/2. So now I have 7 to what power gives me 7 to the 1/2? Well, my answer would then, of course, be 1/2. So that's kind of a nice way to be able to do it when you can. Now we have log base 5 of 1 over 25. So this one's a little trickier for sure. It's got, a couple steps here. But we know that 25 is 5 squared. So I will start with that. I will start by rewriting my inside as 1 over 5 squared. However, that is not enough. My answer is not 2. Because inside the parentheses, I have not rewritten it as 5 to a power. Right now I have 1 over 5 to a power. But I can use the fact that 1 over 5 squared is the same as 5 to the negative 2. And now I have log base 5 of 5 to the negative 2. That tells me my answer is negative 2. 5 to the negative 2 is 1 over 25. That's how I read them. For the next one, we have log base 3, and then inside the parentheses is a 1. And this is a very important logarithm. We want to think about, is there a way to write 3 to a power that gives us 1? And we want to remember that there is an exponent that always gives us 1, and that exponent is 0. So log base 3 of 3 to the 0 is 0. And what that's saying is 3 to the power of 0 is 1. And so 3 to the 0 gives us 1. And so our answer is 0, the exponent. Now, the last one you might be like, man, there's some relationship between 16 and 2 and I'm not sure what it is. Is there a way to write 2 as 16 to a power? So another way to think about this is you could say, well, I want to know 16 to a power, will that give me 2? That's the question being asked. 16 to what power gives me 2? And you can rewrite 16 as 2 to the 4th. So I can rewrite my 16 as 2 to the 4th. Okay. Notice my other side is just 2 to the 1. 16 to what power gives me 2 to the 1? And then using my powers of exponents, because see there's this relationship here between exponential and logarithmic, I get 2 to the 4x equals 2 to the 1. And then I just use the fact that since my bases are the same, that implies that 4x has to equal 1, or x has to equal 1/4. And now I have got my answer, because that is the exponent that I need. So that's kind of a long way to do it. You can actually do this with any of the ones we just did, but they were a little bit easier to suss out on our own. but that's the idea there. Because you're taking the fourth root of 16 and that's giving you 2. So it's an exponent of 1/4. But again, over on the right-hand side, that's a perfectly valid way to get answers if you need to. Okay? That's a way that can work sometimes. So understand that we have some different bases there. You can use any kind of base that is a positive real number. So there's an infinite number of logarithmic functions because they can have all sorts of bases. However, there are two special ones. When you see log base 10, that is a special logarithm, the logarithm with base 10. It is so special that if you just see log, you assume base 10. So although you can have any base, if you have base 10, you'll just see the word log. You have to say, oh, that's base 10 because I just see log. If you see log base e, so this e is coming back to us that we saw in the last section. If you see log with base e, you actually probably won't see log base e because it is so special that instead we say ln. Now, that's because it's considered the natural logarithm. That is why it's called ln. Don't ask me why it's not nl. Don't ask me. I don't know. But it stands for natural logarithm. Over here, we have the common logarithm. So if you have base 10, you have your common logarithm. And you should be able to find on your calculator the log and ln buttons. They are the most common, so you're gonna see them. So for mine, they're right on the left-hand side. I see log and then I see ln. Once you press that, it's already going to have the base in there because it knows that it's base 10 for log and it knows it's base e for ln. And then you can just put in whatever number you see. So we have a couple examples there, one of each, and you can put in your value, in this case 3.6, and you could see if you can get the correct numbers there. So if you're willing to, you have your calculator right there, see if you can plug those values in and get out the correct numbers. Round to 3 decimal places. Okay. And okay. So notice these are different answers because they are logarithms with different bases. So because of that, the exponent that you need to get the thing inside is going to be a different answer if you have base 10 or if you have base e. So there are some properties. I've talked about some of this already. So the ones I've talked about are the first one here. So the first property here, this is really how I've been talking about it the whole time. So the idea there is if you can rewrite whatever base you have, for example, say you have log base 5 of 25, you can rewrite 25 as 5 squared. If you have it in this form, boom, there is your answer. It is the exponent to which you raise 5 to get 25. I've also talked about this one here. This is, for example, we did log base 3 of 1, and that was log base 3 of 3 to the 0. And so that's why it's 0. But the point is it can work with anything. So I could have had 15 here, and if I had 1, the answer is still 0. And log base, it really doesn't matter. Log base 11.2 and then of 1 is 0. So it doesn't matter what your base is. If you have 1 inside, the answer there is 0. Over here, this would be an example like log base 9 of 9. And all you want to remember with that is if I just have 9 inside my logarithm, then it has an exponent of 1 on it because it has no other exponent. So the exponent by default is 1. And so our answer there is 1. And that's going to be true for anything that you have where you have the same base and the same thing inside. The last one is if you have a to the log base a of x, the answer is x. I have an example here that I'll show you, just something so you can kind of see. So if I have, say, for example, 4 to the log base 4 of 16. Okay, so if I have that, then if I think about log base 4 of 16, the question there is 4 to what power gives me 16? That's this piece right here, is 4 to what power gives me 16? We know that that's 2. So I have 4 squared is 16. That's why when you have something of this form, your answer is just the thing that you have inside that upper logarithm. Yay. Okay, just a little bit more here. We have if a is between 0 and 1. So for example, if you were to have log base 1/2 of x, it's possible. So this is saying 1/2 to what power gives you, whatever you have inside. So notice that it looks different. We have this function here, you may remember it. This is 1/2 to the x. So its inverse is actually log 1/2 of x. So you can see that I have that. And what you probably may also notice is that it is symmetric over the line y equals x. That's the idea there. They are inverses of each other. But you can see they have kind of the same shape, but just in a different way because of the fact that the 1/2 to the x is reflected over the y-axis. And so then that thing gets reflected because of its inverse over y equals x, which is the inverse function that you see there. Okay, so we've already talked about what you see on the left-hand side. So this, don't forget, this was section 4.1, so you've already seen all that information about exponentials. What you want to understand with the fact that logs are the inverse of exponentials is you're going to see some similarities and then some like flips and stuff. So notice, as I already said, the domain of our exponentials, all real numbers, and the range is positive real numbers. So that's flipped for the logarithms, for the inverse. The domain is all real numbers, and the range, the domain is all positive real numbers, and the range is all real numbers. So it's that idea of the switch for the fact that they're inverses. The y-intercept is 0, 1, but for the logs, it's the x-intercept. We have no x-intercept and then no y-intercept. And I'll go back to here. So here's our basic log function here. This is log base 2 of x. So just kind of giving you the skinny on this. So as you can see, we have the domain being all positive real numbers, but the range is everything because it goes down and it goes up. We also have the fact that there is an x-intercept but no y-intercept. So you should see that. We do have the x-intercept of 1, 0. You can see that point right there. So this is all stuff that you can see on your sheet here. So just doing the rest of them, we do have a vertical asymptote instead of a horizontal asymptote. So vertical asymptote at x equals 0. So here's x equals 0. So we're going to go along this side there, getting infinitely close to that. And in this case, notice we have log base 2. That's a number that's greater than 1. So our logarithm is increasing in that case. And here you can see that we have a base that is a fraction, and our logarithm is decreasing in that case. Decreasing, going down. And just like exponential functions, logarithmic functions are 1-to-1. They pass both the vertical and the horizontal line test. And so they have inverses, which we know because they're exponential. And then last thing here, just a couple examples of what happens when we take a logarithmic function and do a transformation, which you probably recognize. Hopefully by now. I'm trying not to put them all the same, so you kind of have to think about it. But if we take a look at the first one, I want you to notice we have log base 2, but of x plus 1. So I want you to notice that the plus 1 is inside with the x. So if we want, we can rewrite this as x minus a negative 1. So because it's inside the parent function, so the parent function here is just log base 2 of x. Inside it, we have x minus a negative 1. So that tells us that we have a horizontal shift in this case. And with the horizontal shift, you can probably guess how many units. Horizontal shift, 1 unit. 1 unit, and then that's going to be to the left because x minus negative 1. So it just takes every value and moves it over to the left. So I'm just finding any of these points that kind of fit easily where I can just, but it's just 1 unit, so every point's just 1 unit. And then we're just going to curve it up like this. And we're going to curve it down like this. So the point's 1 unit there to the left. Now the second one you might be able to recognize is you're taking your parent function and then at the end you're just adding 1. So you've got your function values that are going to come out, but then you're adding 1 to them. And so that's going to raise up those y values. So here we have a vertical shift, and not surprisingly, that's going to be 1 unit. And again, you're just adding to the end of your y values. So 1 unit up. So I'm going to take my y values and just move those 1 unit up, whatever I can kind of find that looks reasonable. Okay. So this one's going to just look a little bit different. It's going to have the same asymptotes and stuff. It's just going to be 1 unit up. Okay. So that's a couple transformations with logarithmic functions. Just really remember that if you know the parent function, the transformations that you see are the same. The vertical, horizontal shifts, the reflections, all very similar, just going from the parent function and then putting in the transformation. And that's section 4.3.